So let me ask you a question here. Let's say that you find the derivative of your function and you set that thing equal to 0 and you found yourselves some critical numbers. Do you know whether or not that critical number actually represents a relative minimum or a maximum? No, you do not. All you know is that it is a potential minimum or maximum, which we call a candidate, which brings us to the candidates test, sometimes called the closed interval test because it's testing for the extreme values on a closed interval for a function. So let's take a look at what it says. To find the extrema, that's the absolute minimum or maximum, of a continuous function f on a closed interval from a to b. So remember that according to the extreme value theorem, since we have a continuous function on a closed interval, it's going to guarantee that we have at least one minimum or maximum value. But it doesn't say where they happen. It doesn't say how to find them. Instead, the closed interval test will tell us how to get it. So step one is to actually find your derivative and find your critical numbers. Find your critical numbers of f in the open interval from a to b. How do I find the critical numbers? I take the derivative and I see where it's equal to 0 or where it's undefined. So notice that you're not finding critical numbers at the two endpoints. Why is that? They could be critical numbers, but you're not guaranteed that that's where your derivative is equal to 0 undefined. But those are going to be candidates anyway. Your two endpoints could be where your absolute minimum or maximum values are going to occur as well. All right, so these are also candidates, your two endpoints, your A and your B, as well as the critical numbers that you got from taking the derivative and set it equal to 0 or finding where it's undefined. All right, so now what? You need to find the y values at each of those critical numbers. So you plug each one of those critical numbers back into your original function, and you get the y value that goes along with it. But what are we going to compare those y values to? We've got to compare them to the other candidates, which are the a and the b, the f of a and the f of b, the two endpoints there. So evaluate your function f at each of the endpoints on that closed interval. And so now you have all your candidates for your potential minimum maximum points. How do I tell which one is the absolute minimum or which one is the absolute maximum? Well, at this point, it's going to be painfully obvious because now you just see which is the biggest, that's the absolute maximum, which is the smallest, that's the absolute minimum, and that's it. So just kind of a recap for this closed interval test. Step number one is you have to make sure that you have yourself a continuous function on some sort of closed interval. And when you do, you're going to take its derivative and find the critical numbers. Find it where it's equal to 0 or undefined. Plug those back into the original function, get the y values. Plug the endpoints into the original function to find the y values and find which one's the biggest and which one's the smallest, because those are the only places where our absolute minimum and maximums could possibly happen. So let's put that into practice right here in example 5. Find the extrema of f of x is equal to 3x to the fourth minus 4x cubed on the interval, closed interval, from -1 to 2. Okay, so first of all, can I apply the closed interval test to this, the candidates test to it? I sure can, because this is a cubic function which is continuous everywhere, so therefore it must be continuous on this closed interval. So then, what do I do next? I find the critical numbers. I'm going to find the critical numbers by finding the derivative and seeing where it's equal to 0 or undefined. So f prime of x is equal to 12x to the third minus, another 12x squared. Okay, critical numbers come from where this derivative is equal to 0 or undefined. This one's not going to be undefined because it's a cubic polynomial, which is continuous everywhere. So let's see, I'll bring this down, 12x cubed minus 12x squared. I've got a cubic polynomial that I have to solve, and I'll solve that by factoring. I can pull out a GCF of 12x squared, and then we're left behind with an x minus 1. So I usually abbreviate critical numbers like this. Looks like a C sharp. So our critical numbers happen at x equals 0 from this guy, and x equals, 1 from that one. All right, so now what? I have two possible candidates for an absolute minimum or maximum, but I have two other ones. Where are the other two candidates? Those occur at the endpoints because I could also have minimum or maximums there. So usually I resolve this closed interval test. I conclude it with a table of values. My function was f of x is equal to 3x to the fourth minus, 4x cubed. I wrote that down again because I need to find the y values of all of these candidates and see which one's the biggest and which one's the smallest. I'm going to make a table of values here, like it's algebra 1. I don't know why it's so lopsided. Let's just go with it. Okay, so over here on the left-hand side, I only need to test my candidates. My candidates are my two endpoints, starting with a -1, and all the critical values in between there, which is 0, 1, and my other endpoint was 2. So let's plug those back into the function and find out what the y values are. F of -1. I don't plug it into the derivative. Why would I not do that? Because I just get 0. Well, except at -1 and 2, I wouldn't necessarily get 0 there. I want to see what the y values are on the original function. So 3 times -1 to the fourth minus 4 -1 cubed. -1 to the fourth is going to be +1. That's just going to be a 3. And then -1 cubed is -1 times -4 is a positive. 4 gives me 7. Plugging in 0, that's going to be easy. It's 0, right? 0, 0, it's all 0. Plugging in 1 is almost going to be as easy. 3 times 1 to the fourth minus 4 times 1 to the third. And I get 3 minus 4, which is 1. No, it is not. It is -1. -1. And then one last one. I need to find f of 2. And I could plug that in. 3 times 2 to the fourth, minus 4 times 2 to the third. And I could do the direct substitution like that, or I can do synthetic. Let's do that. Let's give that a try. So I'm going to put this 2 on the outside here, and I have a 3x to the third, a -4x, 3x to the fourth. This one is cubed. I don't have a squared, I don't have a linear, and I don't have a constant term. Bring down the 3, multiply, and I'd have a 6. And add those, a 2, multiply, 4, bring it down. By bring it down, I mean add it, multiply. You get an 8, add it again, 8, and a 16, add these together, I get 16. Do I get 16 from that? I'll let you check it. You probably should. Okay, so let's see. Let's draw our conclusion. So what is our absolute minimum value? So our absolute minimum min at x is equal to 1. But that's not what the absolute minimum value is. The absolute minimum value is actually the y value, which is -1. So that's f of 1 is equal to -1. So that's what the actual minimum value is. And our absolute max value, where does it happen? Our absolute maximum happens at 2. So this is going to be f of 2 is equal to 16. Let's take a look at what this stuff looks like on the graph, shall we? So voila, and we can see here are our endpoints. This one was at 7, this one was at 16. And we did have a critical number here at 0. We had another critical number here at 1. Here's our absolute minimum point down here at 1. And then our absolute maximum happened at that endpoint.